Hey guys, so in this video what I want to explain to you is a little bit about what limits cell size, surface area to volume ratios. And we're going to talk about calculating surface area to volume ratios, what they might ask you on the AP exam, as well as we're going to talk a little bit about metric units and converting between metric units based on the chart that they provide you for the AP exam. So what I'm going to do is share my screen with you. So let me stop this. I'm going to share my screen. And we are going to talk first a little bit about why cell size is limited. So here's the bottom line. And the notes explain that surface area increases by a factor of n squared and volume increases by a factor of n to the third. But what you really need to understand ultimately is just that the surface area does not increase as quickly as the volume. In other words, if you had a cell, just a simple sphere, and I make that sphere bigger, what's going to happen is the surface area, or the exposed surface that can actually, where stuff can actually diffuse in and out. Because remember, in order for something to get to the middle, it only has one path. It has to go from the outside to the center. So as this gets bigger, the distance that it's going to have to travel to get to the center is going to increase. That's the surface area compared to the volume. So as my sphere gets bigger, or as a cube, if you had cube-shaped cells, as they get bigger, what's going to happen is this surface area to volume ratio, the comparison of surface area to volume, is going to get smaller and smaller. And so the more volume you have, the more stuff you have inside the cell compared to exposed surface to get to the middle. It's going to make the cell less efficient as far as getting things in and out. So the cell, if it gets too large, what's going to happen is it's either going to starve to death or it's going to poison itself. And so the cell won't be able to stay alive. Bottom line, the most efficient cell, and when I say most efficient cell, I'm talking about specifically for purposes of transport, not necessarily most efficient for purposes of storage or most efficient for staying warm. I'm just talking about specifically getting things in and out. The most efficient cell is going to be the one with the highest surface area to volume ratio. Now, there are ways that cells can improve this ratio. For example, if you have a cell that's just this big ball, a big sphere, there's going to be a lot of distance to get to the center. But I could have a long skinny cell with the same exact volume inside. It holds the same amount of liquid, but now I've increased its surface area. So the surface area to volume ratio is going to be better. So sometimes changing the shape of a cell, especially to long and skinny cells, would allow cells in your body like muscle cells and nerve cells to be somewhat larger. So let's just talk real quick. Here's kind of a diagram that shows you what happens as a cell. If you just use the same size cell, the rule is as it gets bigger, this surface area to volume ratio is going to get smaller and smaller because volume, this, is going to increase faster than the surface area. So notice what happens. The volume is getting bigger. They're both getting bigger. Don't get me wrong. They both are increasing, but the volume is increasing more to a bigger degree than the surface area is. And so what's happening to the ratio is that it's getting smaller and smaller. The bigger that ratio, the more surface area you have per unit of volume, the more efficient the cell is going to be. Now, that would tend to make you think that the smallest cell is always going to win this battle. But keep in mind that that's only going to be true if all the cells are the exact same shape. So if you were to get this picture, I'll come back to those formulas, on the AP exam, and they asked you which of these three cubes is going to be the most efficient for getting things in and out, yes, your answer is going to be the smallest one. If they were to ask you which of these three spheres, yes, your answer is going to be the smallest one, because we already know the ratio gets worse. It's a smaller ratio of surface area to volume as the size of the cell increases. So your smaller cell is going to win. But what if they give you three cells that are not the same shape? They give you, for example, three rectangles with completely different dimensions. They give you a sphere and a cube and a rectangle. They give you a couple of cylinders that have different dimensions. You're not going to be able to tell just by looking at it which one technically has the best ratio. So they provide you with, on the AP exam, the formula sheet. So the formula sheet has the surface area and volume formulas for a sphere, a rectangular solid, a cylinder, and a cube. So these are all fair game shapes that they could ask you to calculate the surface area or the volume or or they could ask you to calculate the ratio of surface area to volume, and they could ask you which cell is the most efficient. So let's take a look first. Let's try 3 practice problems. So here's 3 cells. They're completely different shapes. You can't really just glance at them and very quickly off the bat say which one is the biggest or smallest or has the best ratio. And let's go ahead and calculate the surface area, the volume, the ratio, and then the question is which one has the best ratio. In other words, which one would be the most efficient for getting things in and out. So the only way we're going to be able to answer that is we're going to have to do the math. So I'm going to walk you through the math. So we're going to calculate the surface area, we're going to calculate the volume, and then we're going to calculate the ratio of surface area to volume. And then what we'll do is we'll basically look at the 3, and whichever one of the 3 has the biggest ratio, that's what we're looking for, is the biggest surface area compared to volume, that's going to be our winner. That's going to be our cell that's the most efficient. So let's look at the first one, a cube with a side length of 5 centimeters. Okay, so surface area of a cube with a side length of 5 centimeters. Our formula for surface area from the formula sheet is 6 times 1 side squared. All right, and again, I'm getting all these formulas right here. I'm not going to scroll up and down just to save a little bit of time, but trust me when I tell you, you can actually just look these up. There's nothing to memorize here. So 6 times 1 side squared is going to be 6 times 5 squared, which is going to give us a surface area of 150 square centimeters. Keep in mind, if you forget your units, they're not going to give you any credit for your answer. So if this is a free response question, you got to include units. Just like I've told you that on graphs, if you forget to label an axis or you label the axis but you don't put the units, they act as if you didn't label it. So they're very, very real sticklers about that. Don't forget your units. It's always going to be squared for a surface area. For volume, it's always going to be cubed. Whatever the unit is, cubed. All right. The volume is 1 side to the 3rd. So that's simply going to be 5 to the 3rd. And that's going to give us 125 cubic centimeters for our volume. Now our ratio would be 150 over 125. And you do need to divide this out and get a number. Don't just reduce this and leave it as a fraction, because remember, our whole goal here is that we've got to compare 3 numbers and we got to pick the biggest one. If you leave this as a fraction, it's going to make it very difficult for you to compare it to the other 2. So if I divide this out, I get 1.2. What does that literally mean? That means, no units here, that I have 1.2 units, whatever units it could be, of surface area per unit of volume. It's a ratio. So my ratio is 1.2 units of surface area per every unit of volume. So I have a little higher surface area compared to volume in this scenario. All right, now my sphere. So the formula for surface area of a sphere is 4 pi r squared. That's going to basically be 4 pi times 2 squared, which is going to be 16 pi centimeters squared. Now, do you have to calculate it, multiply 3.14 as pi? No, not for this. Now, if they just ask you for surface area as a number, you might want to actually plug in 3.14 instead of leaving pi, although I think it would probably be okay to leave pi. But in this scenario, pi is going to end up canceling in the end. I'll show you. So really, don't waste time. You know, you have a time limit on the AP exam. Don't waste time calculating pi. Next, volume is 4/3 pi r to the 3rd. And again, I'll say one more time, you have access to these formulas. You're not memorizing them. That's going to be 4/3 pi times 2 to the 3rd, which is going to give me an answer of, I'm going to round here, 10.67 pi centimeters to the 3rd. All right, apologize, my iPad's glitching a little bit. That's centimeters to the 3rd. All right, so that's our second one. Now we need to divide those out. So 16 pi over 10.67 pi. And you can see now, hopefully, why I did not actually plug in 3.14, because my pi over pi is going to cancel. And my answer here ends up being approximately 1.5. So that's my second one, 1.5 units of surface area per unit of volume. So that's actually better, right? My sphere, so far, my sphere is the winner. It's the more efficient at transport. All right, and last but not least, my rectangular solid. So this surface area formula is kind of a pain. It's length times width times height. It does not matter which one of these you make length, width, and height. Just assign length to one, a width to one, a height to one. That's the easiest way to do it. Surface area is going to be 2 times the length times the width plus 2 width times height plus 2 length times height. I believe that's the way they word it on the formula sheet. You can actually just multiply by 2 at the end as well if you know that formula, but here's the formula sheet one. Okay, so if we plug that in, you're going to basically get 6 times 4 times 2 plus 2, I'm sorry, scratch that. It's going to be 6 times 4 times 0.5. No, I'm so sorry. Done this 4 times today. It's going to be 2 times 6 times 4. I had that right. Plus 2 times 4 times 0.5 plus 2 times 6 times 0.5. So I apologize for all that mess there. But if you multiply all that out, you're going to get 58 centimeters squared. And then my volume is just length times width times height. So that's just going to be 6 times 4 times 0.5. And that's going to give me 12 cubic centimeters. All right. And then if I divide that out, 58 over 12, and I'm going to get a ratio of 4.8 to 1. Technically, all of these are to 1, just to clarify. So that's, in other words, a ratio of 4.8 units of surface area per every 1 unit of volume. So that's another way you could word this. All right, so if I compare my 3, I have 4.8, I have 1.5, I have 1.2. So if I had to rank these cells in order from the most efficient to the least efficient, my best cell would be my third one, has the highest surface area to volume ratio. Number 2 would be my sphere. And then number 3 would be my cube. So you'd put them in order from the best ratio, the highest number, to the lowest. So that's how you'd work these out. Now, shortcuts, just a heads up, if you're good with math, you may have noticed that you could technically calculate the ratio for a sphere in 1 step. It's 3 over the radius. And you can calculate the ratio for a cube in 1 step as well. It's 6 over the length of one side. That's not necessarily going to save you a lot of time, because in some cases they may ask you just for the surface area or just for the volume. But if what they asked you for was the ratio, that would be a quick way to solve it, or even just to double check yourself and make sure that you did it right. Okay, so that's surface area to volume ratios. We're going to move on to metrics. So this is what they provide you with on the AP exam. What they're showing you here is the meanings of the prefixes. In other words, giga means 10 to the 9th. Mega means 10 to the 6th. Mega means million. Kilo means 1,000. So they're giving you what when they say factor, that's kind of like what the prefix means. But what does that mean if you actually have to solve a metric conversion? So a lot of people mess this up because of the way that this table is provided. So what I would recommend, I added the word meter here as sort of a reminder. What this table really means, if you were going to use this to get metric conversion factors, is that there's 10 to the 9th meters in 1 gigameter. So this is 10 to the 9th meters is equal, sorry, my iPad is very unhappy, is equal to 1 gigameter.